Good morning. This is Cody Hendrickson. Today we're going to be looking at what it takes to do sorting objects in Java, starting with the basic sorting algorithms. So we have some of the basic sorting algorithms we're looking at. So we have our loop-based or recursive and our hashtag extra sorts. The loop-based algorithms are the ones you're going to start and design with the most often. So we have bubble sort, selection, and insertion. Recursive algorithms are Mergesort and Quicksort. Those are two of the more powerful sorts we'll be using. And we'll take a quick little cursory look at those today, but we'll look at more detail in another lecture. The hashtag extra sorts we're looking at of Radix and Bogo, we'll see after we get finished with the basic structures. So primitives, when we're sorting primitives, it's really pretty easy because primitives have built into them the support for using the relational operators. So we can use the less than, greater than, less than or equal to, greater than or equal to, equals to, or not equals. And those work almost the exact same way in Java land or computer science land as they do inside regular math land in the real world. So 3 is less than 7, true. 7 is greater than 3,245, false. A is less than Z, well, that's true because the char primitive type A and Z are actually just basically number wrappers. Math.pi, smaller than math.e, false, okay, good. However, we get a little bit weird when we're talking about floating point, aka decimal values. So 0.1 times 3 equals 0.1 plus 0.1 plus 0.1 is going to return false. Now that crazy little meme of the person shaking their eyes is exactly what you should be doing with this because 0.1 times 3 and 0.1 plus 0.1 plus 0.1 do work out in the real world just fine. However, when we're talking about them in floating point land, they don't actually equal the same thing because of the problems of representing values in binary in a floating point math because it's just not going to be the exact same value. We don't know exactly where that difference is going to happen, but it's going to be somewhere after the 0 after the 0.1 that we just specified. So it's up there in that thing. And so in order to make a comparison like that for an equality comparison on a primitive, which we're not really doing when we're doing sorts, we have to make sure we do a subtraction and look at the difference between the two values and then rank based on that. But that's the only thing you have to really do to change that. That's the only big difference about that for floating point math. However, we do want to often, and most actually, we usually are doing things with sorting on objects. And in order to sort objects, we can't use the less than object because it just doesn't work. You can't override the less than operator or the greater than operator work with an object class. So in order to do that instead, we have to implement the comparable interface. Now take a look at the other video I have on how to do comparables to get more detailed directions on how to work with that. But what you have to do is you have to make sure you have a compare to method as part of that. One of the big pros on that is you can give a complex of a comparison or as simple as a comparison as you want to do and make that happen. And so you can make that code be as big or as small as you want it to be for sorting objects. And so we have a quick little example we'll be looking at right here to get just a really simple one. But you can have that be as massively complex for comparisons if you have a really complex object if you want to make that happen. The only con attached to the comparable interface is there's only one comparison level. You can only compare this against that. If you want to do some more advanced comparisons, take a look at the comparator interface. We'll do that inside another video, but that's a bit more advanced topic. So here we have an implementation example of how to do comparable on an object. This is my debug.class, and the two methods you have to look at when you're dealing with the implementation of comparable. So the first one we have is the .equals method. The .equals method takes an object parameter and looks against this one versus the other one. First it checks to see if they're the exact same memory location, and then if it's not the exact same memory location, is it the same thing as a duck, and goes into detail from there. Then we want to have compare to, and this is the actual implementation of that. And if we're doing that, we have compare to debug duck other duck. And if the duck is the same as this duck, sweet, we're good. Otherwise, we compare the question count. Now, the only requirement when we're dealing with a comparable interface is that we explicitly have a negative value for smaller ones and a positive value for bigger ones. The actual values that we use, it doesn't really matter. Now, when you're looking at strings and other built-in structures, they have some really complex doing stuff for how to have that .compare to method, like say the difference between the values of the ASCII approach or the Unicode value. No, we're going to do that a little bit simpler. We're going to do integer.min value divided by 2 because that's negative 1 billion and change. Woohoo! And if it's bigger, we'll return 123. Easy to peasy, we're good to go. Now on bubble sort, I'm not going to go over the actual direct implementation. We're just going to talk about the logic attached to it because bubble sort is probably one of the worst sorts you've ever actually want to do. So bubble sort, you're going to take your structure right here. In this case, I've got some playing cards, and you're going to compare this one to every single one inside the structure and swap every single time you need to. So 4 is bigger than 2, okay, swap. 4 is bigger than king, nope. Okay, 4 is bigger than 3, swap. And then we keep on doing that, and then we swap that one. And so we not that, we not that, we not that, we not that, swap, 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 swap. It's always the worst possible option because we are going over the outer loop and the inner loop, and every time we do that, we have a swap inside the inner loop, so over n squared. It's ridiculously bad. That nested loop structure is really amazing. It's great stuff, but that swap every time there's adjacent value or out of order, we have to swap that, and that's just, oh. And so to finalize this, the last time it's going to go through is after you have your sorted value as you go through the thing. It's like, oh, I'm almost in sort right here. and I'm going to go through, yep, I'm out of order, I didn't swap anything, that's how I know I'm done. And so it's really quite amazing. Now the selection sort is a little bit of a better algorithm. The selection sort is going to find the index of the maximum or minimum, whichever one you happen to be looking for. Usually we're looking for the min though. And you're going to find that index of that, and you're going to retain that index as the value you're going to keep track of. Now, just like bubble sort, the average or worst case on this is order of n squared. So it's not really the best thing to do when you have a large quantity of unsorted data. Instead, we've got other structures that we'll use for that. But the reason we use it is because it's really simple to implement, and it has the same basic structure of nested loops over a structure. Now, as we do that nested loops over the structure, we're going to have the update index of the current min or max inside that inner loop. And then if that min or max is different from the outer loops variable, we'll do the swap algorithm. And that's pretty much standard stuff. So we have right here the selection algorithm. We're using an array structure. And so we have our array of outer loop. Starts off at 0, goes until the array.length, and then it goes up by 1. Inside the outer loop, we have an int index, which starts off at outer loop's variable, so it's keeping track of wherever we are in the outer loop. In this case, right here, so outer loop right here is pointing to the king in this case. And then my inner loop starts off at outer loop plus 1, so I'm going to compare it to the queen. And we go again on that all the way to the end of the structure, because again, we have to loop through all of them. And then we say if myducks at inner dot compared to myducks at min index, which in this case is outer, then I'm going to set my min index, my keeping track of my index, not swapping, to this spot. And I'm going to go and on this point, I'm going to have inner go up by 1, so inner is going to go to 4. Is 4 less than what's at min index, which it is because min index is moved to king, so I'm going to move to the 4. And then repeat that to king. Nope. Is 2. Yes, okay, move min index pointing to 2. That keeps up to there. And then up to the 5. Oh, nope, stays at 2, so right here. So I'm going to take that min index right here, and min index is not equal to outer loop's variable. So I'm going to swap items min and that. And we go right there, and boom. And I repeat that whole process all over again, now starting off at 1, going through, doing that, and swapping as we go through. And so the selection sort, the big way to identify this and what we want to keep track of is we keep track of the index of the current min or max, and then we swap after that. So that's the greatest way to keep track of the selection sort as an algorithm. Insertion sort's a little bit cooler. Insertion sort, we're going to take and we're going to look at the current value we're searching against, and then as we go through it, we're going to build a sorted structure as we go through the list. Now, insertion sort is also order of n squared because, well, it's loop inside a loop, and that's n times n minus something squared is, or insertion sort is still going to be n squared because of an outer loop of n and an inner loop of n minus something. And so n times n minus something is still n squared plus minus some change. But that's okay because it's still n squared. That nested loop structure, though, however, on insertion sort, it's a little bit different. The outer loop is going forward through the structure, but the inner loop is going backwards through the structure because we're building that structure up as we go through. And that's how we're also able to minimize some of the execution time on this, and why insertion sort's a little bit better than the selection sort structure. Now, where we're different also in insertion sort is instead of keeping track of the index of the current min or max, we're going to keep a reference to the actual value stored inside that structure. So we're going to hold on to this, not point to where it is. And so as we go through, we're going to move the values down in the inner loop and replace that outer loop variable. So here we have the insertion algorithm. The insertion algorithm, though, we're taking this one out with a list because, again, these same structures work almost the exact same way. All you have to do is change the way of operating through the structure. So it works with a list or an array or basically any linear data structure. So for int outer is equal to 1, outer is less than randomlist.size, outer plus plus. So I'm going to start my outer up here at this one, and I'll have it stick up a bit. And making sure it's not directly in order, which it happens not to be. Hooray. Okay, so I'm going to start this up. That's at outer, and it's higher than everything else. And then we're going to say that debug duck tested is going to point to this one, so it's a reference to the value stored at that spot. And then int inner is going to be outer minus 1, in this case 0, right here at that spot, and we'll turn it to the side. And then we're going to say inner is greater than 0, or equal to 0, which it is. And tested, the one that we were holding on to with this variable, dot compared to randomlist get inner, though this one is less than 0. Oh, is ace less than 4? And we'll say that yeah, ace is because it's a 1. So if that's the case, then we're going to say yes. Then randomlist.set inner plus 1. So at this spot where we're holding on to right here at outer, we're going to take this value and replace it in at this spot. And that's okay because of a variable holding on to this. So even though I replaced it and it's still sitting over here in that part of the list, I'm going to say inner minus minus, so it's going to go to -1. I'm going to take randomlist.set inner plus 1 and replace that value right here, that ace, at that spot. And so that's where it's a little bit different than selection sort. Instead of tracking the index and moving the swap based on that, I swap every time I need to, going through and build that sort list as I go through the structure. So again, with insertion sort, one of the ways we keep track of it, we have an outer loop going forward and an inner loop going backward, and we hold on to the value itself, not just point to the index. And that's one of the great ways to keep track of insertion sort. Now, there are some really amazing algorithms we'll talk about when we get to a little bit more advanced topic of recursion, but the divide and conquer approach to sorting information is really, really cool because everybody can sort a list if it's one big or too big. There's no real work involved to sort these things. And so by using a divide and conquer algorithm, I can sort the entire deck very easily because I can break it down into really tiny pieces. The way we do that is using the process of recursion, which we'll cover again in the future, but basically the idea is we need to know when to stop at the base case or when to call the same method with a different set of info, aka the recursive case. And the structure of recursive sort is we have a method with some parameters that has an if block inside it. If you're done with the appropriate test, then we stop doing work and we finish building the structure. Otherwise, we break the problem down in half and send these parts to the method again where it can then do the work. The merge sort algorithm is one of the simpler of the two recursive sorts. The merge sort algorithm checks to see if the list is 1 or 2 in size. Well, definitely not in size. So if it's not, I'm going to take this half and this half, split it off, and send it down to the structure. And it's going to send it back to that structure. And if it comes back, then we bring those in order. And it's like, oh, I've now got 2 sorted mini lists, and I can merge these now mini lists together. And that has an efficiency of n log n, which is a way better than n squared. Now, the problem is if I use this on sorted data, I go up to n squared anyway, which, that's not so hot. But that's okay. Quicksort, we'll take a look again at the algorithm for that when we come back. Merge sort, we'll take a look at the algorithm for that when we come back to it. However, when we look at Quicksort, it's a little bit different of a recursive algorithm. The Quicksort algorithm is going to find the structure. It's going to take a look at that, and it's going to put a pivot index, the value that's at that spot. And then everything that's bigger than that goes to the left, everything that's smaller than that goes to the right, and then it repeats that process recursively, and then we have a built sorted list as we go through it. It's kind of like the insertion sort, but in a recursive fashion. It's really pretty cool. But again, just like the merge sort, you never ever want to use this on sorted data because it makes it be completely useless. Now, moving on to the hashtag extra sorts. There are some really other cool, amazing ways of sorting data. We're going to cover 2 of them really fast. Now, the cool way of sorting data is the Radix sort. And this is they put stuff in piles, aka how you've been doing stuff your entire life, because again, computer science really is for all, because you can sort things based on properties and really sort it really quick. Now, you already know how to do this. When you're using laundry, you put the colors, the darks, and the delicates, you split them apart, and then you've got, the towels, they go in there, some special pile, of course, always. But the same way approaching this with Radix sort is with data, we're going to use the least significant digits to the most significant digits. aka we're going to do the zeros, the ones, the twos, and then the zeros column, the tens column, the 20s column, 30s column, 40s column, and the 0-hundreds column, the 100s column, the 200s column, the 300s column, blah, 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 blah. And we can just pick blip, 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 blip like that, and it builds the sort list. It's really pretty cool, and we'll see a great example of that later on. Now, I also have the amazing hashtag extra Bogo sort. Now, it really isn't that hashtag extra. We have our structure, and we're going to do it is we're going to randomize the structure, aka shuffle. Are we in order? No? Okay, we'll shuffle again. Are we in order? No? Guess what we do? Yes, that's right, we shuffled again. Are we in order? Nope. Okay, so we shuffle again. This is the most inefficient way of doing information almost on the planet, but we can actually make this a little bit even worse by doing some other special things. But we also have the amazing power of 50 card pickup, which is actually a better way because when we do this, we're actually more likely to put things in order because we're looking at the information and not just randomly picking things up off the floor. But that's the quick way to take a look at some of the basic sorts. Again, with the insertion sort, the selection sort, those are the 2 we're looking the most at right now. With the selection sort, we find the index of the current min or max. We keep track of that and adjust it as necessary. When we go to the insertion sort, we keep track of the current value and we build the sort list as we go through. And the really quick way also to identify that is we have an outer loop going forward, an inner loop going backwards, and we swap at the end as well. Those are some great ways to take a look at sorting data. Thanks again and have a great day. Goodbye.